Welcome to Math with Professor V. In this video, we're going to learn about solutions about ordinary points. This is video lecture for section 6.3 for differential equations. So now we're going to focus on linear second order differential equations. Remember, they have the following form: a2 of x y double prime plus a1 of x y prime plus a naught of x times y equals 0. And each of these are functions of x, the coefficients on y double prime, y prime, and y. Now we're going to focus on, first and foremost, putting these linear second order differential equations into standard form. So we can refer to them as y double prime plus p of x times y prime plus q of x times y equals 0. And this is simply done by dividing everybody by the leading coefficient a2 of x. Now recall some terminology. We say that a function f is analytic at a point A if it can be represented by a power series in x minus a with a positive radius of convergence. So basically, if at a point A we have a power series representation for a function with a non-trivial radius of convergence, then it's analytic. Okay, and this is what's been allowing us to find power series solutions all along. Now we're going to get a little bit more specific, okay, about what sort of values of A we're interested in looking at with our solutions. So we say that a point x naught is said to be an ordinary point on the differential equation, just again, linear second order, a2 of x y double prime plus a1 of x y prime plus a naught of x times y equals 0 if both p of x and q of x are analytic at x naught. So when you see analytic, you just think, is there a power series representation for each of these functions at x naught? If so, then we say x naught is an ordinary point in that differential equation. If it's not, any point that's not an ordinary point is said to be a singular point of the equation. Okay, so just some new terminology, not too wild, hopefully. Let's go through, look at some examples so you can see exactly what it looks like when you have an ordinary point versus a singular point. Okay, so we have y double prime plus e of x times y prime plus sine of x times y equals 0. Notice this is already in standard form. So e to the x is p of x. And sine of x is q of x. So I want to figure out what the ordinary points are for this differential equation and what the singular points are, if there are any. Okay, so remember the criteria is, do we have power series representation for p of x and q of x with a non-zero radius of convergence? Well, p of x is simply e to the x. And hopefully that one's memorized now, right? Maclaurin series representation, power series representation. So we have 1 plus x over 1 factorial plus x squared over 2 factorial plus etc. And this has radius of convergence of size infinity, yes. And then what about q of x? That's sine of x. Oh yeah, we have power series representation for sine of x. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc., alternating all the odd powered terms with corresponding odd factorial in the denominator, and radius of convergence on that guy is also infinite. So they both have infinite radius of convergence, and that tells us that every finite value of x is an ordinary point. Okay, regardless of what x is, these power series will converge. We have a power series representation for both p of x and q of x on all real numbers. Okay, very good. Now, all right, now we get into a very important theorem that basically allows us to solve the differential equations of this section, the existence of power series solutions. So if x equals x naught is an ordinary point of the differential equation a2 of x y double prime plus a1 of x y prime plus a naught of x times y equals 0, we can always, we love a good always, find two linearly independent solutions, two of them. Why two? Because this is order 2, that's right. in the form of power series centered at x naught. So they would have the form y equals the sum n equals 0 to infinity c sub n times x minus x naught to the n. A series solution converges at least for absolute value x minus x naught less than r, where r is the distance from x naught to the closest singular point, real or complex. So it'll converge so long as we're on the radius of convergence. Here's the method of solution that we're going to apply. First, assume that a solution of the differential equation exists in the form y equals the sum n equals 0 to infinity c sub n x to the n. That's not such a wild assumption if you think about it, because we just require that a function be analytic near a certain point and not too difficult to satisfy for these kinds of differential equations that we're solving. Our goal is to find the coefficients c sub n using the methods of the previous section. You guys are professional by now. You should have this under control. And then the general solution of the differential equation is going to be a linear combination, right, of the two solutions, y1 and y2. So you put the general solution together as y equals c1 y1 of x plus c2 y2 of x. I honestly think this section is going to be a little bit easier in the sense that when you're doing the exercises, you only need to list the first three non-zero terms of each linearly independent solution. So what that means is, unlike the last section, you don't need to find a pattern within the coefficients in order to write the rule and write out your series solution in sigma notation. You're just going to list the first three non-zero terms, put plus dot dot dot, and then move on with your life. So I think it's a little bit easier, okay? Maybe some of the math is a little bit nastier along the way, but not finding the pattern does simplify things for you. If you're not in my class and you have to do more, I'm so sorry. Okay, let's get into it and look at some examples. All right, first example. For each differential equation, find two linearly independent power series solutions about the ordinary point x equals 0. Let's put this differential equation in standard form. Y double prime minus xy equals 0. So x equals 0 is an ordinary point. And in fact, there are no singular points in this differential equation. Okay, don't fret. We will focus on those in the next section. Okay, so remember, we start off, we assume a power series solution exists of the form y equals the sum n equals 0 to infinity c sub n x to the n. These are all going to be second order, so you're always going to need first derivative and second derivative. You might end up memorizing them, or you might want to just jot them down somewhere and keep referring to them. Remember, we shift the index up by 1, so we'll have n equals 1 to infinity c sub n times x to the n minus 1. And then when you differentiate once again, now we shift up to n equals 2 to infinity c sub n times n minus 1 x to the n minus 2. All right, I'm going to substitute those in now, those series representations for y double prime and for y into the differential equation. So now we have the sum, n equals 2 to infinity, c sub n times n minus 1, x to the n minus 2, minus, then we have x times y, which is the sum, n equals 0 to infinity, c sub n x to the n equals 0. Okay, very good. I'm going to simplify, bring this x inside. So we're going to have here, let's just leave this alone for now, n equals 2 to infinity, c sub n times n minus 1, x to the n minus 2, minus the sum, n equals 0 to infinity, c sub n x to the n plus 1 equals 0. Now remember, our goal that we went over when we were finding power series solutions in the last lesson is to have the power on x match on both these terms. So what I'm going to do is shift the index of summation here. If I want this to be n plus 1, it needs to go up by 3. So all of my n's I'm going to replace with n plus 3. And then I would need to start 3 lower. So I'm going to have to start now at n equals negative 1. So n equals negative 1 to infinity. Then this becomes c sub n plus 3, n plus 3, n minus 1 is now n plus 2, and then we have x to the n plus 1, minus the sum n equals 0 to infinity, c sub n x to the n plus 1. Okay, perfect. So now that these powers on x match, woohoo, we turn our attention, we need to start at the same value for our index of summation. So since this series is starting one lower at n equals -1, I'm going to pluck that off, write the n equals -1 term separately, plus, and then start at 0. That way they'll both be starting at n equals 0. So if n is -1, we're going to have c sub 2 times -1 plus 3 is 2, -1 plus 2 is 1, and then this is going to be x to the 0. This all corresponds with n equaling -1. Plus, now that term's taken care of, so I'm just going to start my series at 0. And then everything else is the same, right? So I didn't lose a term, I just wrote it separately from everybody else. And then, finally, we have x to the n plus 1 in both of these, and they both start at n equals 0. And remember, the whole point of doing that is so we can factor out. We want to factor out the sigma and x to the n plus 1. So let's just clean everything up. This is going to be 2c2. Everything else is just a bunch of 1s. Plus, then we have the sum. N equals 0 to infinity. Let me put all the coefficients together. So c sub n plus 3 times n plus 3 times n plus 2 minus c sub n times x to the n plus 1 is 0. How are we doing? Okay, good. Now, in order for all of this to be 0, because x cannot be 0, that means this coefficient must be 0. So c2 is 0. And then also I can set c sub n plus 3 times n plus 3 times n plus 2 minus c sub n equal to 0. Always solve for c sub whatever's higher in terms of c sub n. So c sub n plus 3 is going to be c sub n divided by n plus 3 times n plus 2. Okay, good. So now we're going to use this to list out the coefficients for the first few terms. We should have 2 power series solutions, okay? And one will be dependent on one coefficient, the other will be dependent on the other coefficient. You'll kind of see how this all plays out in just a minute, okay? Don't fret. The first time it's maybe a wee bit frightening. We need more room. Certainly we do. Okay, so start off, we're going to plug in n equals 0. Okay, so I'm going to have C3 equals C0 over 3 times 2. Okay, so that's just going to be C0 over 6. And then this would be the coefficient on, do you remember? It would be the coefficient on x cubed because you look at the subscript here. All right, keep going. N equals 1. So that would be C4. That equals C1 over, n is 1, so this is 4 times 3. So this is C1 over 12. That's the coefficient on x to the 4th. Now notice I'm just multiplying everything out because I'm not worried about finding a pattern for any of the exercises in this section. N equals 2. Keep going. So C5 is going to be C2 over 5 times 4. But you guys, isn't C2 0? Yes, don't forget. C2 is 0. Oh, okay. So then this is just 0. So we have no x to the 5th term. Interesting. Okay, n equals 3. N equals 3. So that would give me C6. That's C3 over 6 times 5. Oh, but I have C3 already. Look, look, look. C3, it's right here. It's C0 over 6. So that's C0 over 30 times 6. So that's C0 over 180. And that would be the coefficient on x to the 6th. Very good. Very, very good. Let me scoot this down so I can scoot the page up. And then you can still see the formula. Okay, perfect. Okay, let's do one more. Actually, no, we'll do quite a few more. Okay, n equals 4. That's going to give me c sub 7. So that's c4 over 7 times 6. Well, let's see. C4, oh, I have it right here. C4 is C1 over 12. So C1 over, this is going to be 42 times 12, right? C7. So that's C1 over 504. And that's the coefficient on x to the 7th. So do you see a little pattern emerging? The terms are either dependent on C0 or C1. Okay, they're either dependent on C0 or C1. Keep going because I need the first, however many. I said 3 non-zero terms. I'm going to do 4 because I'm such a show-off, okay? 3 or 4. Just do whatever I specify in the homework instructions. Keep going. N equals 5. N equals 5, so that would be C8. That's going to be C5 over 8 times 7. Oh, but C5, do you remember? C5 is 0. So this is just 0. Okay. N equals 6. That's C sub 9. So that's C sub 6 over 9 times 8. But we have C sub 6. It's right here. C0 over 180. So this is C0 over 72 times 180. That's the coefficient on x to the 9th. This ends up being C0 over 12960. This is coefficient on x to the 9th. Okay, no surprise. That one's dependent on C0. So I've got 1, 2, 3. Don't forget as well. So here's x cubed, x to the 4th. There's no x to the 5th. X to the 6th, x to the 7th. There's going to be no x to the 8th. Here's x to the 9th. What about x squared? Well, that one's going to be 0 because remember C2 is 0. So x squared is just not going to appear here. Then C0 x to the 0, that's just C0, that's a term. And then C1 x to the 1st, that's another term. So notice here, all the terms that are dependent on C0, I'm highlighting in green. All the ones dependent on C1, I'm doing in this orangey color. I've got so far this freebie, and then 1, 2, 3, so we're good. And then this is not really a freebie, so here's 1, 2, 3. Let's get one more so we match up. Okay, n equals 7. So C sub 10 is C7 over 10 times 9. Do I have C7 somewhere? Yeah, it's C1 over 504. So C1 over 90 times 504. This is C1 over 45360. Whew. And then that's the coefficient on x to the 10th. Okay. Very good. If you wanted to do a few more, n equals 8. Then you would have C11, and that's C8 over 11 times 10, but C8 was 0. Okay, I think we have plenty, okay? Let me start putting everything together. So y equals C0, I'm going to do it in increasing order, plus C1 x to the 1st, there's no C2, then C3 is C0 over 6 x cubed, C4 is C1 over 12, x to the 4th, no C5. C6 is C0 over 180, x to the 6th. C7, C1 over 504, x to the 7th. There's no C8. C0 over 12960, x to the 9th. C10, C1 over 45360, x to the 10th, plus yada, yada, yada. Okay, now here's where things get interesting. They're either dependent on C0 or C1, so group them accordingly and then factor out those constants. So I can factor out C0 from all of these terms here. Yes, and then you're left with 1 plus 1/6 x cubed plus 1 over 180 x to the 6th plus, and I'm not making you find a rule or pattern for the coefficients, so you can just stop like this. And all of this is my y1 of x plus, and then we have c1 as the coefficient, or as part of the coefficient on all of these terms here, so I can factor it out as well. And then you have x plus 1/12, yes, x to the 4th, plus 1 over 504 x to the 7th, plus 1 over 45360 x to the 10th, plus yada yada yada. And who is this? This is our y2 of x. Okay, very good. To see the full video lecture on this topic, you'll need to become a member of my channel. To join, head to a desktop or laptop computer. Usually a tablet doesn't work. And on any one of the videos, just find the join button or go to the membership tab here. You can also join my Patreon in case you don't have access to YouTube membership in the country that you live. But either way, there's always a way to access these differential equations, linear algebra videos, and more exclusive content. Thanks so much for your support. Bye!